Hello everyone, I'm Rajasri, Assistant Professor of Department of EEE, working at MLR Institute of Technology, Hyderabad. And in the last session, we have seen Introduction to Power Electronics, and today we will be discussing SCR, what are the different modes of operation, static VI characteristics of SCR, and various turn-on methods of SCR. First prototype of thyristor was introduced in the year 1957. Firstly, what is the abbreviation of SCR? It is Silicon Controlled Rectifier. You may ask me a question, is SCR and thyristor one and the same? SCR is a device which comes under the thyristor family, and there are many other devices which comes under the thyristor family like GTO, gate turn-off thyristor, MCT, MOS controlled thyristor, and IGCT. There are many other devices which comes under the thyristor family. And SCR, it is a semi-controlled device. As I have already explained in the previous session, it is semi-controlled. It is because if you see here, it is just similar to that of a diode, and it has got anode and cathode terminals, and along with this, an additional terminal will be there in SCR, that is gate terminal. So, we can apply the gate to cathode pulse, and we can in turn control the output voltage which is actually fed to load. And that is the reason during turn on time, we can control the turning on of the SCR, whereas there is no control over turn off time. So, that is the reason SCR, it is termed as semi-controlled device. SCRs are solid-state devices. They are compact, possess high reliability, and have low losses. Similar to the advantages of power electronics, since this is a power electronic device. SCRs of voltage rating 10 kilovolts and an RMS current of 3000 amperes with corresponding power handling capability of 30 megawatt are available. If you see, like diode, SCR also allows current flow only from anode to cathode, whereas it blocks the current flow in the reverse direction. Unlike diode, SCR has also the capability to block the current from anode to cathode until and unless it is triggered into conduction by gate signal. So, this is how it is different from that of a diode. And it is a semi-controlled device. And this is the structure of the SCR, and this is the symbol of a SCR. It is a 4-layered PNPN device, and it has got 3 terminals, namely anode, cathode, and gate. And it is a 3-junction semiconductor device. Junctions namely J1, J2 and J3. And usually gate terminal will be placed closer to that of the cathode terminal. Fine. What is the condition for SCR to conduct? It is junctions J1 and J2 and J3 need to be forward bias. This condition need to be satisfied in order to bring the device into the conduction state. What is the basic principle of operation? Whenever anode and cathode terminals are connected to main power circuit, whereas gate terminal is connected to control circuit, in that case, possibly 3 modes of operation can be obtained. One is reverse blocking mode, forward blocking mode, and other is forward conduction mode. Firstly, let us see reverse blocking mode. That is, when anode is made negative with respect to cathode, in that case, junction J1 and J3 will be reverse biased, whereas J2 will be forward biased. Hence, SCR does not conduct any current through it, and it simply acts as open circuit. It is because, see, junction J1 and J3 are reverse biased, only J2 is forward biased. Let us explain this with the help of a equivalent circuit so that it will be more understandable. Here, this is say junction J1 which is reverse bias. That means it is an open switch, open circuit. This is J1, and here junction J2 is forward bias. That means it is short circuit. It is represented with a short circuit. And then we have junction J3. Again, it is reverse bias. That is represented with a open circuit. And this is connected to negative terminal, other positive terminal. So this is how the equivalent circuit looks like. And if you see, since J1 and J3 are open circuited, the device does not allow any current flow through it. That means it is simply an open switch, or it can also be considered as an off switch. So during reverse biased mode, the device will be acting as an off switch. However, small amount of current flows due to the minority charge carriers. Yes, though device is in off condition, due to the minority charge carriers, there will be certain amount of current which is flowing through the device, and this is termed as reverse leakage current. And if in case, what happens if the gate pulse is applied in the reverse bias mode? We should not apply. What if we apply? In case if we apply the gate triggering pulse, in that case, junction J3 will be forward biased, but SCR will be in the off position, and which increases the power loss. It in turn contributes to the power loss. See here, when gate triggering pulse is provided, junction J3 will be forward biased. That means it will be short circuited. But J1 is still open circuit. That means there will no current flow through the device. That is the reason SCR is termed as off switch. And since we are unnecessarily wasting the gate triggering pulse, that is the reason it contributes to the power loss. And we should never apply gate triggering pulse during the reverse bias mode of operation. And then we'll see forward bias mode of operation, forward blocking mode of operation. Forward blocking mode of operation, whenever anode is made negative with respect to cathode, in that case, junction J1 as well as J3 will be forward biased, whereas J2 will be reverse biased. In this case, let us draw the equivalent circuit. See, first thing, J1 and J3 are forward biased. That means there is only certain J2 is reverse biased, in the sense there is certain amount of depletion layer which is actually present. So this depletion layer, it is acting as a potential barrier. Potential barrier in the sense it is acting like a wall in between, and it is not allowing any free flow of the electrons through it. So that is the reason this will be in off state. That is, in the forward blocking state, the device is ready to conduct but not at conducting state. Ready to conduct in the sense, if we can break this particular depletion layer, in that case, it allows free flow of electrons through it. So that is the reason it is ready to conduct but not at conducting state. So here what happens? SCR does not conduct any current through it. Yeah, we can also explain this using a equivalent circuit. That is, junction J1, it is short circuited. Junction J2, it is open circuited. This is the depletion layer. And then we have junction J3, which is short circuited. Anode is made positive with respect to cathode. And if you see, since J2, it is open circuited, it does not allow any current flow through it. That is the reason the device is said to be in off state or ready to conduct state. So now, due to depletion layer J2, which is formed, there will be no current flow through the device. However, small amount of current will be flowing through the device. That is due to the forward leakage current. That is nothing but forward leakage current. This current is due to the minority charge carriers. Next is, we have forward conduction mode. That is, when anode is made positive with respect to cathode. In that case, again, junction J1 and J3 will be forward biased, whereas J2 will be reverse biased. So, because when anode to cathode voltage, if you see here, J1 as well as J3 is forward biased, but J2 is reverse biased. That is, J2 is forming a depletion layer over here. That means it is acting as a potential barrier, stopping the current flow through the device. If we can break this particular junction somehow, in that case, we can bring the diode into the conduction state, as I told you previously. So for that purpose, what we do is, we will be increasing anode to cathode voltage. Anode to cathode voltage greater when compared to that of forward breakover voltage. In that case, width of the depletion layer at junction J2 reduces. It actually gets narrowed down. In that case, at some particular voltage, if we go on increasing this particular anode to cathode voltage greater than forward breakover voltage VBO, in that case, at some particular voltage, this particular depletion layer gets break. And this phenomena is called avalanche breakdown. And the voltage at which avalanche breakdown occurs is called VBO. That is forward breakover voltage. So, as junctions J1, J3 are already forward biased, and because J2 breakdown has taken place, that means there is no barrier as of now. There is no barrier as of now, and because of which this device allows forward current flow, free carrier movement of the electrons through the device, and that is how the device comes into the on state at particular voltage called VBO, which is also called as forward breakover voltage. Now, junctions J1, J2, J3, all the three are forward biased, and it is allowing the current flow through the device, and device has come into the on state. Fine. How to bring this particular device into the off state? By reducing the current below that of holding current, we can bring the device into the off state. These are the static VI characteristics of an SCR. If you see, when anode to cathode voltage, forward anode to cathode voltage is applied, in that case, what happens? Anode current, forward current, anode current starts building, and this is the forward leakage current which is actually flowing through the device. As I told you, though the depletion layer is existing, even in that case, there will be certain amount of leakage current which will be flowing through the device because of the minority charge carriers. And that is the reason this is nothing but forward leakage current. Now, device is ready to conduct, but it is not at conducting state. And if at all, if we are increasing this particular voltage greater than forward breakover voltage, in that case, we can bring the thyristor into the conduction state. And this is the forward on state current or forward conduction current. And if you see in the reverse blocking mode, similarly, certain amount of leakage current will be flowing through the device, and later, if accidentally the voltage increases beyond certain limit, in that case, it conducts current through it. And further clearly, we will be discussing these static VI characteristics in further slides. What are the various turn-on methods of SCR? How we can actually bring the thyristor into the on state? So these are the various methods which we are actually following. That is forward voltage triggering, gate triggering, temperature triggering, light triggering, and dV by dt triggering. Forward voltage triggering. Whenever anode to cathode voltage is increased beyond forward breakover voltage with gate circuit open, avalanche breakdown of junction J2 takes place, at which the voltage at which avalanche takes place is called VBO, that is forward breakover voltage. So here in forward voltage triggering as well, junction J1 and J3 will be forward biased, whereas J2 will be reverse biased. So if we can, by some means, if we can break this particular reverse bias junction J2, in that case the depletion layer, the potential barrier will be vanished, and thereby it will allow the free flow of electrons through it. So here in forward voltage triggering, we are actually increasing the anode to cathode voltage beyond the forward breakover voltage. That is, anode to cathode voltage is made greater when compared to that of forward breakover voltage. In that case, junction J2 will be broken down. So this phenomena is called avalanche breakdown, and the voltage at which avalanche breakdown is actually taking place is called forward breakover voltage. So at VBO, SCR changes from off state to on state, and where junction J1 and J3, they are already forward biased, and now J2 allows free movement of carriers across 3 junctions. As the J2 is being broken up, as a result, large forward anode current flows through the device. This method of turning on of the SCR is called forward voltage triggering. But the thing is, exceeding VBO is never employed in practice because it can actually destroy the device. See, usually the magnitude of VBR as well as VBO is nearly same. In fact, VBR, the reverse breakdown voltage VBR, is usually slightly greater when compared to that of VBO, but VBO will be taken as the final rating of the SCR, and even while designing, VBO will be taken as its final voltage. So it will be designed for VBO, and now if anode to cathode voltage is increased beyond VBO, in that case it will actually damage the device. And after avalanche breakdown, in that J2, it also loses its reverse blocking capability. So this is the disadvantage associated with the forward voltage triggering. So that is the reason increasing this particular anode to cathode voltage beyond VBO is not a healthy method. So here, okay, fine, we can turn on the thyristor like this. How to turn off the thyristor in this case? Thyristor can be turned off by making anode current less than that of holding current. If you can bring the anode current lower to that of the holding current, in that case, we can actually turn off the thyristor. This is the gate triggering. Gate triggering is the second method how we can actually bring the thyristor into the on condition safely. As I told you, during forward conduction mode, forward voltage triggering, it is not the healthiest method in order to bring the thyristor into the on state, since J2 is losing its capability to block the reverse current during its operation. So that is the only reason gate triggering is simple, reliable and efficient, and this is the most usual method in order to turn on the thyristor in the safe mode. Voltage greater than normal voltage is applied with gate circuit open. In that case, SCR remains in forward blocking mode. As I told you, forward blocking mode is the mode where device is ready to conduct but not at conducting state. That means J1, J3 will be forward biased, whereas J2 remains reverse biased. And if we can break this particular J2 by some means, we can bring the thyristor into the on state. So when turn on is required, in that case, a positive gate pulse voltage between gate terminal and cathode terminal is actually applied. So now charge carriers are injected into the inner P layer. That is this PN device when gate to cathode terminal is applied, in that case, charge carriers are injected into this particular inner P layer, where this is the depletion layer which is blocking the current flow through the device. So when this particular inner P layer is flooded with electrons from cathode, as a result, width of the J2, it becomes narrow. It gets reduced. So because of the already existing depletion layer, when these charge carriers are actually reaching the depletion layer, the number of collisions takes place. And because of this number of collisions, actually the vanishing of this particular depletion layer takes place. Vanishing of this particular depletion layer takes place, and because of which J2 will be completely vanished. I am using the term vanished. Previously in forward voltage triggering, it has been broken. That is, depletion layer has been broken. Whereas here, we are bringing the thyristor into the conduction state in the safest mode by vanishing the depletion layer. Because of the number of charge carriers accumulating nearby depletion layer, collisions takes place, and ultimately the depletion layer has been completely vanished. That means bringing the thyristor into the conduction by the safest method. So this causes now J2 to break down, at which VBO, that is forward breakover voltage required, is reduced, causing J2 to break at a voltage less than that of forward breakover voltage. Now, the forward voltage at which device switches to on state depends upon the magnitude of gate current. So, the higher the gate current, the voltage required in order to turn on the thyristor will be reduced. If magnitude of gate current is increased, more electrons will increase J2. As we go on increasing the gate current, more electrons will be reaching this particular junction J2. So, in that case, the J2 width will be reduced, and finally it will be disappeared and it comes into the on state. So J2 SCR gets triggered at a lower applied voltage. So higher the gate current, lower the VBO required. That means we are bringing the thyristor into the conduction state with less forward breakover voltage. In turn, we are actually protecting the thyristor and operating it in a safe mode. And if you see here, IG1 is greater when compared to that of IG2. IG1 is greater when compared to that of IG2, and IG2 is greater when compared to that of IG3. If you see here, IG3, in case of IG3, this is the forward breakover voltage which is required, and if we go on increasing the gate pulse width, that is the magnitude of gate current at IG2 is more when compared to that of IG3. At this instant, the voltage required to turn on the SCR is less. And in case of IG1, the current is further more when compared to that of IGO, and the voltage required, the forward breakover voltage required in order to turn on the thyristor into the on state is further less. And finally, this gate pulse is now required, is sufficient in order to bring the thyristor into the on state, and finally the thyristor is conducted, and this is the forward conduction mode current. So this is how we can bring the thyristor into the on state using gate current. Gate current magnitude will be about 20 to 200 milliamperes. This is the magnitude of the gate current required to turn on the SCR. When gate current is removed, the conduction of current from anode to cathode remains unaffected. That is, while providing the gate triggering pulse, it need to reach certain current called latching current. Latching current, this is nothing but the latching current, and this is the minimum value of the current. This is the minimum value of the current in order to bring the thyristor into the on state. And if at all, if the gate pulse is provided and if it has not reached the latching current, in that case, if at all, if we are removing the gate triggering pulse, in that case, thyristor will come into the off state again. So that is the reason while providing the gate triggering pulse, we need to make sure that it has reached certain value of current, so-called latching current. And if latching current is being reached, in that case, thyristor will come into the on state. And even if we remove the gate triggering pulse after having reaching to latching current, the thyristor still remains in the on state. And how to bring the thyristor into the off state is, holding current is the minimum value of the current to keep the thyristor into the on state, below which the thyristor will be in off state. So this is the holding current. And below, reducing the current below to that of the holding current, it turns off the SCR. And always the latching current will be greater when compared to that of the holding current in practice. Because latching current, it is associated with the turn on process, whereas holding current, it is associated with the turn off process. And usually this latching current will be 2 to 3 times of that of the holding current. So latching current is greater when compared to that of the holding current. Hope you understood this gate triggering method, which is very important. Next is, we have temperature triggering. During forward bias state, most of the applied voltage is appeared across the junction J2. If you see here, J1, J2, J3, J1, J3 will be forward bias, whereas J2 will be reverse bias because of the depletion layer. So when the forward voltage is applied, the maximum voltage which is applied will be appeared across the junction J2. So because of the applied voltage across this junction J2, it leads to the leakage current flow through the device. And because of the leakage current, it actually increases the temperature of the junction. So when temperature is actually increased, in that case, the further increase in leakage current takes place. And this is the cumulative process. So in this case, what happens is, more number of electrons will actually reach this particular junction J2, and number of collisions takes place, and finally the disappearing of junction J2 takes place. The depletion layer gets disappeared completely, and because of which it allows free flow of electrons through it. But this is not a preferable method to turn on the SCR, as self-destruction of SCR may take place. And this method is called thermal runaway. And increase in temperature, it also damages the device, and which is not a suggestible method. And then we have light triggering. So for light triggering of an SCR, a recess or notch is actually made in the inner peel layer. When this particular recess is irradiated, if the intensity of the light thrown on this particular recess exceeds a certain value, forward bias SCR will be coming into the on state. So light is used to turn on the SCR and allows the current flow through it. And here in light triggering, we use light activated silicon controlled rectifier, that is LEC02, to trigger or turn on the SCR. And in some cases, we can also make use of gate triggering in combination with light triggering and trigger the thyristor in a more effective way and in a faster way. And this kind of combination will be usually used in HVDC. And this is very powerful triggering process. We already know gate triggering is a efficient method in order to turn on the SCR, and this is actually combined with this particular light triggering. And then we have dV by dt triggering. See here, junction J1, whenever anode to cathode voltage is applied, when anode is made more positive with respect to cathode, in that case what happens, junction J2 as well as junction J3 will be forward biased. Is it not? Now anode is made positive with respect to cathode and J2 is open circuited. So in this case, whenever anode to cathode voltage is applied, J1, J3 forward bias and J2 is reverse bias. In that case, this particular J2 will be acting as a capacitor. And J1 and J3 are acting as plates of this particular capacitor. In that case, the current through the capacitor is given by I is equal to C dV by dt. So, as we go on increasing the voltage, that is, voltage is changed with respect to time, we are increasing the dV by dt. In that case, what happens? The current also increases. And since current is increasing, the number of charge carriers also increases. And because of which, the more number of charge carriers are actually injected at this particular junction J2. In that case, more number of collisions takes place and the depletion layer is actually disappeared. So in that case, what happens? Junction J2 gets reduced and finally depletion layer gets disappeared, thereby facilitating the flow of current through the device. And in turn, the device is actually turned on. But this rate of change of voltage with respect to time, dV by dt, is not suggestible method because it is also termed as unwanted or false triggering, and resistor acts as external path for this particular leakage current. See, in order to limit this particular leakage current, we will be connecting the external resistance such that the temperature as well as the extra current which is actually flowing through this particular device can be limited. So that is the reason dV by dt is not a suggestible method. And the upcoming topics in the next session, we will be discussing dynamic turn on and turn off methods of SCR. Thank you.